In this video, we're going to do an example of a singular value decomposition. The first step to a singular value decomposition is to find the value, or to find the matrix A transpose A. A transpose A is equal to 3, 4, 0, 5 times 3, 4, 0, 5, which gives us a matrix. 3 times 3 is 9, plus 16 is 25. And then we get 20. And then by symmetry, we get 20 again. And then in the far right corner, we get 25. Next, we need to find the eigenvalues and eigenvectors for A transpose A. So we're looking for a determinant of 25 minus lambda, 20, 20, 25 minus lambda equals 0. So this is 25 minus lambda squared minus 400 equals 0. And this gives us lambda squared minus 50 lambda minus plus 225 equals 0. And this factors to lambda minus 45 and lambda minus 5. So our eigenvalues are lambda equals 45 and 5. Those are the two eigenvalues that we want to start with. These are going to help form our sigma matrix. So we'll come back to that in a minute. When lambda is equal to 45, our eigenvector comes from the matrix. 25 minus 45 is negative 20, then 20, then 20, then 25 minus 40 minus 25 minus 45 is negative 20. Okay, and so this gives us the relationship x is equal to y, which gives us the eigenvector 1, 1, and we want to normalize that. So we'll multiply by 1 over root 2 because the length of that vector is root 2. Excellent. So this gives us our first eigenvector. Our second eigenvector comes from lambda equals 5. This gives us the matrix 25 minus 20 is, 25 minus 5 is 20, then 20, then 20, then 25 minus 5 is 20. Xy equals 0. So here x is equal to negative y. And our eigenvector here is 1 and negative 1. And we'll, again, normalize it by multiplying by 1 over root 2. Okay, so these give us the start of what we need for our singular value decomposition. Okay, this will give us our right singular vectors and our singular vectors, or singular values. Now we need to worry about the left singular vectors. Our left singular vectors come from taking 1 over the root of the first eigenvalue, which we're going to call sigma 1, times A times V1 in this case. So let's just backtrack a sec. If these are the values of our eigenvalues, this tells us that sigma 1 is root 45, which is root of 9 times 5, or 3 root 5. Our sigma 2 is going to be root of 5. So it's just the square roots of the eigenvalues. So here, we know that sigma 1 is 3 root 5, so 1 over 3 root 5 times matrix A times V1, which is 1 over root 2 times 1, 1. Okay, so we've got this root 2 times root 5. That's going to give us a root 10. We're going to get 3 plus 1 is 3, cancels with that 3, so it's a 1. We get 4 plus 5 is 9, cancels with that 3, gives us a 3. 1 over root 10 times the vector 1, 3. Our U2 then is 1 over sigma 2, a V2. So sigma 2 is root 5, so we've got 1 over root 5 times our matrix A, 3, 0, 4, 5. Times our vector V2. V2 is 1 over root 2 times negative 1, 1. Okay, so once again, you see we've got a negative, we've got a root 2 times a root 5. That's going to give us a root 10. And we've got negative 3 on the top, and minus 4 plus 5 is positive 1. Okay, so let's start putting these matrices together. A is going to be U sigma V transpose, where U is equal to 1 over root 10, 3 over root 10, negative 3 over root 10, 1 over root 10. Sigma is a matrix made up of these little sigmas on the main diagonal. So 3 root 5, 0, 0, root 5. And our V transpose, let's find our V first. Our V is made up of the eigenvectors. So 1 over root 2, 1 over root 2, negative 1 over root 2, 1 over root 2. And so V transpose then is going to be 1 over root 2, 1 over root 2, negative 1 over root 2, 1 over root 2. And so if we multiply this out, we end up with, not U, A. I didn't meant to do it like that, but it worked. So this guy here is U, this guy here is sigma, and this guy here is the transpose of V. And so multiplying those out, you get matrix A.